And we're recording. Wonderful. Okay, so solutions. If you follow along with gases, solutions are just the next down in energy state molecules, and there are a lot of similarities, honestly, in how they act. So you'll see a lot of similar type of concepts when we're doing those, as we are doing these. And there is my classroom. Wonderful. Okay, so solutions are mixtures of two or more substances. We generally think of solutions as being liquids, but they can also be gases. That's what I tell you. There are crossovers between gases and solutions. We are going to identify the difference between the solute and a solvent in solutions, both gaseous and liquid, how you form solutions, the electrolytes and non-electrolytic solutions, what solubility is, saturated versus unsaturated, ionic or soluble and insoluble, concentration, and now we'll start getting into our math. We're looking at concentrations, conversion factors again. Of course, you never get away from conversion factors. Be able to calculate concentrations if you're given the volume and the molarity of a solution and it's diluted, and be able to differentiate between colloids, suspensions, and mixtures. And lastly, how the particles affect osmotic pressure, which I think you will see. Yeah, we looked at when we looked at red blood cells. So we'll be revisiting red blood cells and osmotic pressure. And if you remember when we were looking at osmotic pressure, we saw it all the time, especially when we were looking at the kidneys and absorption in the digestive system. So we'll look at more of the actually chemically what's going on physically to develop these osmotic pressures. Okay. Solutions can be liquids, gases, or solids, I guess. Generally don't think we're looking at liquids and gases for the most part, especially liquids. And they're a combination of solvents and solutes. And solutes are simply the part of a solution that is there in a lower quantity. And I'm not going to get any more technical on that, but just think of that. The solute is dissolved in the solvent. They give an example here of copper sulfate. That's copper 2 in this case. And the copper sulfate will dilute in the water, which is a solvent. Solvent being the universal solvent on our planet, but all kinds of things can be solvents. These are examples of air, liquids, and solid solutions. Okay, the solute and the solvents in this case. So in our atmosphere, oxygen is a solute, was solvent, because remember, nitrogen was north of 70% concentration in our atmosphere, and oxygen was in the vicinity of 20%. So in that case, oxygen is the solute in the solution that is our atmosphere. Okay, so water. We are always looking at water. And just to kind of tickle your memory banks here, if you remember when we were looking at water, and I just want to check and see if we had anyone else join our trying to get in. Nope, no Alejandro. Okay. If anyone hears Alejandro or knows anything about Alejandro, if you could just let me know. I'd appreciate it. Okay, so water, of course. If you remember, there is a difference in electronegativity, developing it in making it a polar molecule. So a partial negative charge. You would love my feedback. Well, not right now. And a partial positive charge out here, because the differences in electronegativity between oxygen and hydrogen. Okay. Hopefully you remember that. All right. There we are. So essentially, oxygen's pulling on the shared electrons more strongly than the hydrogen molecules, making it giving it a partial polar negative around the oxygen, partial positive around the hydrogens in water. Okay. So in solutions, these are some examples of solutes that have exceeded their ability to be dissolved in the solvent, so they settle in the bottom under the influence of gravity in a solution. We'll see, that will be an important idea to keep in mind when we get to the end of lecture on this topic tomorrow. We can always remember, rule of thumb, just like oil rig and oxidation and reduction, mnemonic, or just a concept to remember, is like dissolves like. Okay, and all that means is that if you have a polar solvent, you can dissolve polar molecules, polar solutes in that. Okay? Solutes, there we go, solutes, in a polar solvent. You cannot dissolve a non-polar solvent in a non-polar solute in a polar solvent. I hope I said that right. So, like dissolve like. So, you can dissolve polar solutes in polar solvents to make a solution, and likewise, if you have a non-polar solvent, you can only dissolve non-polar solutes. Of course, okay, and cannot dissolve polar solutes. Okay, so hopefully I'm tickling your memory once again about the difference between polarities, okay, and what that will look like chemically. Okay, and essentially what's happening is that the polar solvents have the partial charges. You have charges in the stored in the ionic bonds that we studied earlier, and you can pull apart those ionic bonds and make a solution. Okay. Okay, so we'll start with like one of the easiest ones, dissolving sodium chloride or table salt in water. Sodium chloride is, of course, an ionic bond between sodium and chloride. They get pulled apart by the polar molecules of water right there, and you can get a bunch of sodium and chloride as individual molecules in solution in water. Okay, so like, dissolve, like. Polar solvent, polar solute. Okay. Another example would be the one of the more simple organic compounds, methanol. It's just a carbon with 3 hydrogens and a hydroxyl or OH group. I don't expect you to know that now. I'm just kind of planting that seed in your mind. And it is polar, of course, because you have, again, oxygens pulling a partial negative towards the oxygen, and that will be able to dissolve polar solvents to form an ionic solution. Okay, so let's just look these over really quickly here. When you have 2 grams of sugar and 100 milliliters of water, of course, the solute is sugar. It's a much lower quantity. 60 milliliters of ethyl alcohol with 30 milliliters of methyl alcohol. The solute is methyl alcohol. It's at half the quantity of the ethyl alcohol. Okay, 150 or 55 milliliters of water, 1.5 grams of sodium chloride. The solute is sodium chloride. And to throw in a gaseous solution, we have 200 milliliters of oxygen and 800 milliliters of nitrogen. The solute in this case is the oxygen. Okay, not too bad right here. Not too mathy, just conceptual. So let's kick it up a notch and look at which of the following solutes will dissolve in water. Of course, we know that like dissolves like, so all they're really asking us is which of these molecules are polar. Okay, so sodium sulfate, we know we have the polyatomic atom of sulfate right there, along with 2 sodiums. So we know that that is a polar molecule and it will dissolve in water because water is polar. Gasoline just tells us right there that gasoline is nonpolar, so that will not dissolve in water. That's why you see oil slicks floating on top of water instead of mixing with it. Okay, or oil spills, somewhat topically as well. Oil spills don't mix with ocean water, so it floats to the top and it gets all over sea life because gasoline is nonpolar and water is polar. Of course, iodide gas is nonpolar, so it will not dissolve in water. And of course, hydrogen chloride is very polar and will rapidly dissolve in water. Okay. Okay, electrolytes versus non-electrolytes. Okay, this is where it's things that clinically this becomes important. You hear about electrolytes in Gatorade or whatever and how important they are. Of course, so this is what this actually means when you see that. And this is not just the marketing ploy where you replace your electrolytes or whatever, but they're anything that is that has dissolved into polar molecules in your system. Okay, sodium, potassium, chloride, bicarbonate, all these things that we did talk about and things that can be measured on a CBC, complete blood count. Okay. So the strong electrolytes are the ones that basically they hit water and dissociate at 100%, okay, such as salt. Sodium chloride dissociates into sodium and chloride, and you can test this by running an electrical current between a cathode and an anode, cathode being the positive bar over here, the anode being the negative. So if you look at your car, where you see your car battery has a cathode and an anode. So the cathode is generally red. It's the positive in your car battery. The negative is the anode. So if you're jumping your car, don't switch positives and negatives. Always go positive to positive and negative to negatives. And you can thank Mr. Mott if you didn't know that, so you don't short out your battery next time you need to jump someone's car. Okay, and that's the reason you're doing it. Okay, they dissociate completely. So it's very easy to electrons. The cathode is the positive and the anode is the negative. Yeah, cathode. And you can remember that because anode is A negative right there. So weak electrolytes dissociate at a much lower pace. So hydrogen fluoride, you still keep some hydrogen fluoride in solution. Hydrogen fluoride is neutral, so it's not going to be conductive. What you want is that dissociated hydrogen and fluoride, and you can get some current to pass through a solution of hydrogen fluoride, but not nearly as much as a solution of sodium chloride. And non-electrolytes, these are nonpolar molecules that do not dissociate in water, such as the sugar sucrose. Okay, you just have particles of sucrose that stay negative, and you get no conduction through a solution of sucrose in water. Okay. Okay, so there's a little chart where it condenses all of that information in one spot. Okay, so let's do some sort of quick review of some of that. Okay, of what we saw. So let's see. What would calcium chloride dissolve to in water? So calcium chloride is definitely polar. So in water, so we know that calcium is in the group 6. Text. Oh no, excuse me, group 2. So +2 cation, and we get 2 chloride ions to balance that out. So that's going to be a strong electrolyte. Lots of calcium and chlorides in solution. And here we have potassium and the polyatomic ion phosphate in water. Of course, polar, like dissolves light, polar will dissolve that. So you know that each one of the potassium is going to dissociate with a charge of 1, with our phosphate with a charge of -3. And so that's what that will look like in solution. Let me make sure I got those right. Okay, I did. And just to check our understanding of this concept, which is following is a strong electrolyte in water. Okay, so combination of nitrogen and water, so those are actually going to come together. We don't have any ions in solution. Likewise with, I guess that is methanol. Okay, state in solution, so nonpolar. And there we have the dissociation, of sodium and sulfate into 2 sodiums and a sulfate in aqueous solution. Polar, so we can probably stop right there. The last one is just some alcohol that has not dissolved at all. So we know that C is the one that's going to be a strong electrolyte in water. Okay, so they're asking us to write down for this dissociation of potassium chromate in water. All they're asking us to do is exercise our knowledge of this polyatomic, the chromate. So we know that that's polar. Water is, of course, polar. So we get 2 potassiums and a chromate, which has a charge of a -2 to balance that out. Okay, partial dissociation. This one's a little tricky. So it's telling you right out of the gate, this is not going to dissociate completely. It's going to be a weak electrolyte. So that comes off. PO4 balances that out. No, let me check that one. How did they want to say that? Yeah, so weak electrolyte, not a strong dissociation. And then certainly, last but not least, we'll just solid sugar, sucrose, table sugar, dissolves. It is a nonpolar molecule. It's just going to stay sugar. And so it's going to stay as sucrose, glucose, sucrose, C12H22O11, and doesn't go any changes in water. Okay. None of the bonds are broken. It does go into changes; they get smaller, but they're still molecules of sucrose. Okay, none of those bonds are broken in water because it is a non-polar molecule being dissolved in a polar one. Okay. Last concept that we're going to look at today before I let you guys do your assignment, go into Blackboard, tell me a little something you learned, study, you know the drill at this point. And I think I will start with this tomorrow too, because it is a pretty important one clinically, is the idea of equivalence. Okay, so an equivalent is a measure in a solution, a polar solution, and electrolytes, and how much charge there is. Okay, so the amount of charge. Okay, it's not just how many molecules, but the amount of charge. And for each +1, +2, +3, -1, -2, -3, you're going to increase the number of equivalents per molecule or atom. So let me show you what that actually means in practice, okay? So they always balance out. Positives and negatives always balance out. Okay, so on the table, look past the bullet points there and look down at the table, and we have sodium. Okay, with an ionic charge of, course, 1. So if you dissolve that in water, it's going to give you 1 equivalent. Okay, calcium has a charge of +2. You get 2 equivalents. Iron can give you 3 equivalents, etc., etc. Of course, the negatives gives you 1 equivalent, is negative. And polyatomic sulfate will give you 2 equivalents, a measure of how much charge you're getting out of that. Okay, and the other thing to remind you, you're going to keep those balanced in any solution. So where we see that in blood plasma, we have a combination of sodium, potassium, magnesium, calcium. Those are all the positive or cations. You have a total of approximately 150, 150, 150 milliequivalents. Okay, on the positive side, that is balanced out by all the negatives, the chlorides, phosphates, proteins, all that stuff balances out with all the negatives. So you have 150 positive milliequivalents, 150 negative milliequivalents in blood plasma at healthy levels. Okay, balance out positives and negatives. Again, chemistry, we're always talking about balance. So some things that you might see in rotation, especially if you go into another field like maybe nursing, it's possible, anything could happen. They talk about 0.9%, that is normal saline, right? That's a rehydration. It has 154 balanced milliequivalents between sodium and chloride. So that's not going to cause, your blood's going to not react to that. And we'll see that when we're looking at red blood cells. But normal saline is what's called isotonic, approximately 150 milliequivalents. Potassium chloride only has with 5% as well. Ringers, all of these are coming in at about 150. About 150. okay, for normal saline, which is 0.9% saline as well. It happens to be the percentage of salt you put in it to get 150 milliequivalents. Okay. So to reiterate, in 1 mole of iron with a 3+, you will have 1 mole will give you 3 equivalents, right? Because you get 3 for every atom of iron. You won't have 1 equivalent for 1 mole. You will have 3 equivalents, 3 positive charges. Okay. In 2.5 moles of sulfate, how many equivalents would you have? So 2.5 moles, and for each sulfate you have 2 negative charges, so you are going to need to multiply 2.5 times 2 to get the number of milliequivalents or equivalents, which is 5. Okay, measure the charge, follow the charges times the concentration in moles, and that will give you the equivalents. And we have an IV bottle with sodium chloride in it. If the chloride has 34 milliequivalents, okay, that means to balance out the negative, you're going to have precisely 34 milliequivalents of sodium to balance it out. Negative 34 plus 34. Okay, so 3, 5, and 3. Good. And I think that's a good place for us to kind of stop for today.